38 meters beneath the floor of the English Channel, in total darkness, a machine the length of 2 football fields grinds forward through solid rock. Above it, tankers and ferries cross unaware. Ahead, somewhere in the blackness, another machine is cutting toward it from the opposite coast. For centuries, the 21 miles of water between England and France was a barrier that shaped wars, trade, and identity. Engineers had dreamed of tunneling beneath it since the age of Napoleon, sketching plans for horse-drawn carriages under the seabed. Every attempt before the 20th century stalled on money, politics, or fear. By the 1980s, technology had finally caught up with ambition. In 1986, Britain and France signed a treaty to build a rail tunnel under the channel, funded not by governments, but by private banks and construction firms, taking an enormous gamble. No public money would pay for it, and none would guarantee its success. The geology beneath the channel was the key to the whole enterprise. A layer of chalk marl, laid down some 90 million years ago, ran in a continuous band beneath the seabed from Folkestone to Sangatte. It was soft enough to bore, yet impermeable enough to keep the sea out. Engineers mapped that layer for years before construction began, drilling boreholes from ships anchored above the strait. Every core sample told them how deep to dig and where the rock might crumble or flood. The tunnel's entire route was drawn from data pulled out of the seabed, one narrow cylinder at a time. In December 1987, construction began simultaneously on both coasts. Not one tunnel would be built, but 3. 2 rail tunnels for trains running in opposite directions, and a smaller service tunnel between them for ventilation, drainage, and emergency escape. Together they would stretch 50 kilometers, with 38 of those kilometers running under the seabed itself. 11 tunnel boring machines were built for the project, some of the largest ever constructed. Each one combined a rotating cutting head with a factory behind it, grinding rock, removing spoil, and installing concrete lining rings in a single continuous operation. Some machines weighed over 1,000 tons and stretched longer than 2 football pitches. The British and French teams worked from opposite ends, each boring toward the middle of the channel, with no way to see or speak to the other. Success depended entirely on mathematics. Surveyors on both coasts had to align 2 shafts dug through nearly identical rock, so their tunnels would meet within centimeters after crossing many kilometers of open sea. Guidance came from laser-based surveying systems that tracked each machine's position to within a fraction of an inch. Small errors compounded over distance were the greatest fear. A miscalculation of even a few degrees over many kilometers could send 2 tunnels drilling past each other in the dark, never to meet. Behind each machine trailed a rolling factory nearly a kilometer long, conveyor belts hauling away crushed rock, workshops fabricating concrete segments, and rail lines feeding in fresh lining rings. Thousands of workers lived and labored in these moving underground cities, breathing filtered air pumped from the surface. The excavated chalk marl, millions of tons of it, had to go somewhere. On the English side, spoil was mixed with water and pumped out to reclaim land at the base of Shakespeare Cliff, creating flat ground that did not exist before digging began. On the French side, spoil was used to build an artificial platform south of Sangatte. Water was the constant enemy. Under the seabed, the machines faced fractured zones where the chalk gave way to sand or flint, and where seawater pressure could force its way into the workings. Engineers used ground freezing techniques and injected grout ahead of the cutting head to seal off unstable ground before advancing. Ventilation shafts, sunk from the surface, fed fresh air deep into the workings, while pumps constantly removed water that seeped through despite every precaution. At its lowest point, the tunnel runs about 75 meters below sea level, deep enough to stay within the safest, most stable rock the geologists had found. On the 1st of December 1990, a moment years in the making finally arrived. A British and a French tunneler broke through a final wall of chalk in the service tunnel, reaching across the gap to shake hands, the first physical link between the island of Britain and the European mainland since the Ice Age. It was a moment of profound symbolism as much as engineering. For the first time in over 10,000 years, since rising seas had severed the land bridge that once joined Britain to Europe, a person could walk, uninterrupted, from one to the other. The breakthrough was broadcast to both nations as a shared triumph. The two main rail tunnels broke through soon after, each guided into alignment with the other after tens of kilometers of independent boring. When surveyors finally measured the gap between the British and French bores, the horizontal error was measured in centimeters, a testament to years of painstaking calculation. Lining the tunnels required hundreds of thousands of precast concrete segments, each one manufactured to exacting tolerances and bolted into place, ring by ring, as the boring machines advanced. The result is a smooth, continuous tube capable of withstanding the immense pressure of rock and seawater above it. Once the boring was complete, an entirely different phase of construction began. Rail track, overhead power lines, signaling systems, and cooling infrastructure had to be installed along the full length of the tunnel before a single train could safely pass through. The tunnel's three bores are connected at regular intervals by cross passages, allowing air, service vehicles, and in an emergency, people to move between them. The service tunnel doubles as an escape route, engineered so that no traveler is ever more than a few hundred meters from a path to safety. Massive ventilation systems keep air moving through the tunnel, managing heat generated by trains and controlling airflow in the event of fire. Two underground crossover chambers, among the largest artificial caverns ever excavated in Britain and France, allow trains to switch between tunnels for maintenance without ever surfacing. Above ground, entirely new terminals rose to handle the tunnel's traffic. At Folkestone and Cocales, vast marshalling yards were built to load cars and trucks onto shuttle trains, while at Calais and near London, new stations were constructed to handle the high-speed passenger service. The tunnel officially opened in May 1994, after 7 years of construction and a cost that ran far beyond original estimates. It stands as one of the most expensive infrastructure projects of its era, built almost entirely by private financing rather than government funds. Two kinds of trains use the tunnel today. High-speed passenger trains carry travelers directly between London, Paris, and Brussels in a little over 2 hours, while shuttle trains carry cars, trucks, and coaches through the tunnel loaded onto open rail wagons, letting drivers stay with their vehicles the entire crossing. A crossing that once took hours by ferry, at the mercy of weather and tide, now takes about 35 minutes end to end. Millions of passengers and vehicles pass beneath the channel every year, moving through solid rock at speeds that would have seemed impossible to the engineers who first surveyed it. The tunnel also carries an unglamorous but vital cargo, freight. Long trains loaded with goods move continuously between Britain and mainland Europe, part of a supply chain that depends on the tunnel functioning every hour of every day without pause. Safety systems built into the tunnel are constantly monitored. Fire detection, ventilation control, and emergency response teams stationed at both ends, ready to respond within minutes. The tunnel has weathered fires and mechanical failures over its history, each incident reinforcing engineering standards that continue to evolve. Maintenance never stops. Engineers regularly inspect the concrete lining, the rail systems, and the pumps that keep water at bay, working through the night in the narrow windows when trains are not running. The tunnel demands constant vigilance to remain as solid as the day it was completed. The tunnel boring machines that carved the passage were, for the most part, never brought back to the surface. Several were driven into purpose-built chambers off the main route and abandoned in place, entombed forever in the rock they had spent years cutting through. More than a century after engineers first dreamed of tunneling beneath the channel, the project stands as proof that geology, patience, and precision can overcome even a sea. It reshaped how two nations relate to one another, collapsing distance into minutes. Somewhere beneath that same stretch of water, trains still rush through the darkness every few minutes, following a path first traced by drill cores and laser beams decades ago. The sea above rolls on, indifferent, unaware of the tunnel of chalk and concrete threading silently beneath its floor.